Hello, we're getting started. Hello. We're getting started, getting the lighting figured out. We will be discussing this right here. We will continue. I hope that people are going to be joining very soon here. I'm just getting my situation figured out here with the live and the settings. Hi, Reese. Reese, how are you? How are you doing? Let's see. So on Do Not Disturb. Okay, perfect. We are on Do Not Disturb. I'm good. I have been a little under the weather, but I think I'm hopefully good, recovering. Not too bad. Okay. Can you see me and hear me okay? I think that's what I want. Okay, and I want the lighting. Okay, perfect. Let me grab a water and then I'll sit down. I just fed the kitty cats their snack. I'm gonna actually change their water as well and get myself a water and then sit down and get started with our live tonight. How is your baby boy? Reese. How's your little baby? Put the laptop here as well. Good morning to the UK and Europe, Africa, everywhere that is ahead in time. Good morning to you, my loves. Good morning. Goody morning. Charlie, he's fine, thank you. Oh, how nice. That's sweet. That is so sweet. Everyone I know is having a baby currently. You're one of them. And that too, a very small baby. A very tiny baby. So I need to change the title of the live and all that. I'll do that when I sit down. I'm just making sure that it gets up on the live monitor. Turn on. I have a few things. He's fine, thank you. I'm taking him to see my dad. Oh, nice. Like and sub. Everybody, when you join, please do like and share and subscribe. Especially please subscribe so I can see you in future lives as well. That would be so very nice indeed. He's all smiley at the moment, it melts my heart. Aww, babies do like my voice. And I'm sure he likes you, Reese, the daddy. Okay, Fuji, let's have your water set up, and then I'm gonna get my water set up and then sit down for our session. Physics live session. Hi, show no morning. Mama loves you more than anything in this universe. Here's your wawa. Oh, Fuji, do you want the bucket water? they have been enjoying water from a bucket during these winter days. So I think I'm gonna do that actually for them really quickly. You want bucket water, Fuji? He wants bucket water. He wants bucket water. He does. He wants bucket water. Fuji, Mama's gonna do. Here, Fuji. So I did this water in a normal bowl and also in a bucket because currently that's what they enjoy. Are you a... They seem to be like a horsey. They're like a horsey. Here, I'll show you. He wants the water in a bucket, so he's waiting for the bucket to fill up and then it'll be set up. Okay guys, I will be right with you sitting down. Thank you guys so very much. Yeah. Don't go anywhere. We're just getting started. Can you please like and share and subscribe? Can we get 20 likes? Oh, Fuji. Who's Mama's good boy? Is it Fuji? Is it Suji? Or is it Baji? It's all of them. It's all of them. An extremely good boy has been found here. An extreme good boy. Extreme good boy. Okay, Fuji. It's almost full. We're gonna put this down for you so you can have bucket water. Come, Shona. Come, Shona Mono. Come, Shona Mono. Drink some water. Hydration is key. This is true. I'm gonna get set up with water. We're gonna have water filled up and then we'll sit. I didn't think they put enough pictures of Einstein on that book cover. Right? There is a lot of Einsteins on this book cover. Please do like and share, guys. Like and share and subscribe. Tell your neighbors, daughters, lovers, boyfriends, girlfriends, them friends that we're live. We are live. We are live. We are live, 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 live. And we will be singing as well. make sure everybody has water. It has been so dry here. It's so dry. Our hairs and furs are so dry. We put some coconut oil in our hairs and furs, but it's still so dry. We have to drink enough water. That's for sure. Enough water must be had. Must be had. Okay, are my lights on? 1, 2, 3, 4. Oh my gosh, Baji's on a top tier. Hi, Baji. Hi. Hi, Baji Baba. Hello, Mr. Baj. Baji Baba is ready for you guys. Thank you so much for being here. If you're seeing this as a video upload, then please do leave me a comment so I know you were here. And, oh, whoops. So that I know you're here and that you caught the live and the video and leave your thoughts and comments. There's Baji behind me. Hello, everybody. Hello. It said there was 30 people, then it suddenly dropped to 5. That's okay. Where are these 30 people? Come back. Come back. Come on back. We are live. Can you please like the live? Sorry, I took a shower and I didn't finish brushing my hair, so I'm doing that real quick. Otherwise, it gets very tangly because it's probably gonna dry by the time the live is done, because our lives go pretty long, and it's gonna be very difficult to brush then. Reese, did anyone say hi? Or is it just you and me saying hi to each other? From Barcelona to, where are you again? Belgium. Okay, so we will get started with the topic of tonight. Hopefully, I'll see many of you joining at some point or other. And hopefully, many of you will find and like this live and like the discussion of tonight, which is basically a continuation from last time. We were on the topic of quantum mechanics, and especially how quantum mechanics developed in the 20th century, along with other things like relativity, which is, of course, to include special theory of relativity, general theory of relativity. One second, is the light on? Is the light on? Is the light on? Yes, there's a light. I'm operating with less light, so there is some shadows and things happening, which is not the most ideal, but we will make it work. So we spoke about basically how, along with special theory of relativity, general theory of relativity, and even sort of the the beginnings of string theory, with the extension of general theory of relativity to having one more spatial dimension by Kaluza and Klein. There was, of course, also a lot of development in quantum mechanics, which really shook the landscape and shook people's minds a lot. And indeed, there were some debates and things like that that we were getting into as far as the next part of that history. So let's see. There's 5 other comments. Oh, actually, I didn't see the comments. Let me catch up. Sometimes, okay, hello Sam VR, hello Key West, hello Top G, hello Jane Doe, Hello, Key West again. All messages. What does that mean? Hi, Vincente. Vincente, how are you? Greetings from Chile. I don't speak English, but if you can message me here and I'll use a translator. Thank you. You're beautiful and have a lovely smile. Well, thank you so much. So actually, let me do the following. Let me make sure that this live is properly set up. Hi, Sachi Mama. There's a weird setting that says top messages or all messages. Hello, everybody. Can you see the live? Welcome, welcome. Please do like, share, and subscribe. We're getting started with our topic for tonight. Please do say something in the chat so we know you're here. Hi, Moo99. Hello, Vincente. How are you doing, guys? Oh, God. I'm still getting a little bit adjusted and ready to rock and roll here. Please do send some love and encouragement. That would be most appreciated at this time while we uncertainly proceed forward. Hello, Ava. Ava Snyder is saying hi. First name, last name is saying hi. Haven't seen you in a while. Hello, Brian MCG. Brian is saying hello, Brian here. Okay. I see some of you. Thank you so much. Please do show some love. I love the hearts that are floating up. Thank you, everybody, for being here. Please do subscribe. We are a Cats and Physics and My Face channel. As in we show kitty cats, we talk about physics, and it's my face that's presenting all of the material. So hopefully you like it, and hopefully we will chit-chat. Welcome one and welcome all to the channel and to this live. Tonight's topic is quantum mechanics, and we are going to continue from the last time when we actually started the topic already, and we spoke up to Heisenberg's uncertainty principle, and there is a lot more very exciting material after that which we will cover tonight. Sorry it's a little late and people may not be in the mood for quantum mechanics, but I promise this is going to be the most interesting live stream of your life. The live of your life. So I hope you are ready, guys. I hope you're ready. Brian, you've spelled your name as brain. Oh, Brian is a brain. That's okay. Brain is good. Thank you so much for liking the live. Blazer is saying Bemba. Well, hello, Blazer. I've been through a wormhole. Oh, hello. Hi, Blazer. Hello, chicken. Goodness gracious. Everybody, please do like and share and subscribe, my darlings. And do not be too weird. There is a moderator here, and he will probably ban you. So try to be nice, kind, polite, well-mannered, and engage in some good conversation here, okay? That would be most amazing, guys. Most amazing. We will proceed with a passion now into physics. This is what we cover on this channel. And currently we're on quantum mechanics. Panhandle of Texas. I went 25 miles in less than a minute. Okay. Hello, Blazer. I'm not sure exactly what that means. Is that a cycling race? Hi, Ray. Hello, the king. Can you smile as wide as you can and raise your eyebrows? I don't want to put wrinkles on my forehead, darling. Unless I smile naturally, you'll have to just make do with my face as it is currently, my darling. Hello, Ray. Hello, the king. Hello, Jeremy. Your wife is beautiful. Okay, very nice, Jeremy. A Chicken is saying physics is such a hot topic. Unique is saying I have a channel also and have subbed you. Oh, thank you so much, Unique Videos, for your Chanel. Hello, Blazer. Hello, I am Kaylee Grace. Do you believe in God? That's great. What a nice question. Shall we discuss that in more detail towards the end of the live? How about that? Currently, we will be discussing physics and other topics, and saying hi to everybody and saying hello to everybody. Please do like, share, and subscribe, my darlings. Oh gosh, these comments are passing by and I'm not even seeing all of them. Sorry if I missed something from you guys. Support me also, sis. Of course, my darling. Unique videos, can you please comment on one of my videos later on so that I can check out your profile then, because I'm a little bit busy right now. But please do leave a comment somewhere on my videos later on so I can go find your channel, okay? Hello, the king. Hello, JACM. By the way, guys, I have a super chat goal and also gifts are most welcome. And I will do the top fans list in just a minute here. JACM is saying hello. Hello, JACM. Hello, Joe Matthew. Joe Matthew, how are you doing? Can physics explain the human body design? Hello, Peter. I'm not sure about that. Human body design, not sure. Hello, Ray. I was here a few weeks ago. It was great hearing your mind work. Oh, thank you. Do you ever get wild and crazy? Hello, KJ. Oh my gosh. Reaching Grace. Are you the person who is pregnant that I ate that pregnancy sandwich for? Oh my God, Reaching Gracie is here. At one point, we did a pregnancy support live. Did you block me, says Pops. I did not block you, but depending on how you behave, the moderator might time you out. But I think so far you're good. So Pops is here. Tito Burrito is saying you're beautiful. Thank you. Adler is saying hi. Tune 3 is saying hi. I want to be where you are. Okay. Hello, John T. Johnson. Have you ever read the Bhagavad Gita? That's a great question, and I think that's a great book. I have not read it cover to cover. I've read parts of it. Brass Monkey is saying hi, beautiful. Tweetu is saying something which is a little weird. Blazer is saying, when I was made, they broke the mold. How old are you? Hello, Brass Monkey. Hello, Pops. Reaching Grace. Oh my gosh, girl. I hope you stay for the live. We're going to discuss quantum mechanics. I think you'll like it. I think you said something like your grandfather did astronomy and that you also like astronomy and you would like to get into it. Well, we're going to cover a very interesting topic in physics today. I feel like I'm very red today. My lips and my sweater are all extremely red and Christmas colored. But oh well, I'm balancing it out with a little bit of black colors as well here with my hair and whatnot. So I am so happy you're here, my darling Reaching Grace. It was so very, 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 very nice the other time when you were here. Reaching Grace did a number of super chats and really supported the channel. And we had a lot of fun with her pregnancy chat during her late night pregnancy related cravings. And I ate sandwich after sandwich to support her. So, and to just in general dedicated the whole live to pregnant women. So KZLI 2010 is saying Indian woman with British voice. Okay. Hello, KZ. Rami Denham is saying hi. Jimothy is saying hi. Hello. Cuanto y apagas live. I don't know what that means. Are you asking what time is the live starting or I don't know. Hello, David. Hello, Johnston. Don't move. Lettuce? Okay. I found out the gender of my baby. Oh my goodness, Reaching Gracie. Well, congratulations. Do you want to share? Have you ever took? No, I have not, Blazer. I am an Irish person, just reading it now. Oh, nice. Are you talking about the Bhagavad Gita? Can you briefly explain quantum mechanics? I will absolutely explain quantum mechanics, but probably not very briefly. The whole live is going to be about it. Hello, Neer. It's very nice. Okay. No weird. I actually don't even know what this 67 thing means. Peter is saying, not sure if you talk and we listen or we ask questions. We will be doing both. Okay, so if you have questions, just put them in the chat and also get to know each other, make friends, and keep on keeping on and dominate the chat and like, share, subscribe. And we will look at the chat as well as take questions, as well as we will actually just cover the material, okay? Shu Do is saying, do you have a formal education in physics or just general interest? I have both, my darling. Abraham is saying, beautiful. Kilo, that's for you, Maud. Oh, it's a boy. Reaching Grace. Everybody congratulate Reaching Grace. She is pregnant with a boy. You don't know Spanish. I only know a little bit. I'm interested if they will ever get a quantum transistor working. The lipstick color looks great on you. Oh, thank you. I put it put this lipstick on, but wasn't sure exactly what it would do. I think it matches the sweater, and thank you so much. Reese is saying, congrats, Reaching Grace. Do you like wearing turtlenecks? I do have some turtlenecks for the winter time. I guess I like them when I need to be warm. Studied thermodynamics. What that dark matter do? Oh, by the way, I think I have to change the title of the live. We're actually going to be talking about quantum mechanics, not dark energy, but that was the default title that I picked. What's the biggest bug you've ever stepped on? Oh my goodness. When do you start? Just very shortly, darling. Keep hanging in there. Can you sing a song by request? You can certainly request a song. We might sing it towards the end of the live, okay? Can you tell a joke? Okay. Hi, Jay Richard. Hi, Andrew. Let me go a little quicker. Hello, Albert. Please do like. Yes, thank you so much for liking the live. Hello, Shudo. One Texas, hello. J Richard, hello. G Miller, before she checked the baby was a superposition. Oh, I love that. We're gonna be talking about something like that tonight. Can you you should definitely tell us a quantum mechanics joke, J Richardson. I'm going to delegate that to you. Hello, John Null. Neurons activated. Good. Thank you. Well, I'm actually very tired, so I just wanted to pop in and say hi again. Good night, everyone. You can leave this on in the background if you'd like. Refrigeration. Can you please give me a shout out? Hello, Zach Mason. How are you doing? Hello, Goldberg. Hello, Ray. Hello, Jimothy. Okay. Everybody, welcome one and welcome all to all of my continents and all of my people. Thank you so much for joining. I really appreciate it. Please do like, share, and subscribe if it's your first time. This live may be a little confusing, like what is going on, but generally on these lives, on these live streams, and on this channel, we cover physics, astrophysics, cosmology, astronomy with my face and my voice presenting. And we also show kitty cats sometimes. My children are cats. And I just have this passion for teaching and presenting physics topics that are pretty advanced. My favorite ones being the ones I just mentioned, astrophysics, cosmology, things like that. My PhD is in particle astrophysics. And lately, we've been covering the 20th century, which is, of course, a very rich time in physics, quantum mechanics, relativity, and things like that all came out of that period. And, of course, kind of culminated in giving us something like superstring theory towards the end of that century, as well as particle physics and lots of discoveries in those types of things. And certain predictions of the 20th century, such as in general theory of relativity, came true as an observed reality, 100 years later, for example, when we directly measured gravitational waves for the first time. So that is to say that that particular century, the 20th century, there were so many amazing things happening and getting discovered and developed that sometimes we are still actually kind of catching up in experiment and measuring those things and confirming predictions from that time. And so the other thing is we've also talked a lot about sort of some differences between classical physics and quantum mechanics, and how those two can have certain disagreements, especially by classical physics, I mean, in the old days, it used to be the Newtonian mechanics and those types of things. But then, of course, as you know, as you might know, gravitation got updated, upgraded, and became sort of the more latest and greatest version of it, and explanation of it was given by Einstein with his general theory of relativity. This also happened in this same time period in the 20th century. After giving us special theory of relativity in 1905, he gave us the general theory of relativity by 1915. So pretty early on in the century, we already had a brand new way of understanding gravitation with a new kind of mathematics and geometry called Riemannian geometry, as opposed to Euclidean, where we're basically utilizing 4 space-time dimensions. So 4-dimensional geometry where there's 3 spatial dimensions and 1 time dimension. And basically, all of the definitions like metric, geodesic, all the Einstein equations, and how gravitation and everything is treated is given sort of a very new look and feel. But at the same time, some of the thoughts and some of the thought experiments and ideas that are behind such mathematics and such formalism is actually some really basic and simple stuff that he had very deep insight on, Einstein, of course. So sometimes we have mentioned about that, and some of the topics we've been covering lately have been touching on these things. So all of this actually belongs to what we call classical physics. So in other words, it could be something like physics of the big stuff, so physics of macroscopic systems, physics that describes, for example, really simply put, say, equations of motion for a larger body. So you, me, cars, the moon, the sun, astronomy, those types of things. Generally, we either describe with Newtonian mechanics and the laws of gravitation given to us by Newton, or if we want more accuracy, more precision, we might go with general theory of relativity. But those are the classical physics that will describe these bigger things. On the other side of this physics of the big is the physics of the small, or the physics of the quantum things, or tiny things. So these are quantum scale things, which are generally considered subatomic level scales, very small particles, electrons, atoms, what's inside an atom, subnuclear, because we used to think that there is the atom as being the fundamental unit of matter, but turns out the atom has an electron. Well, at least this is the hydrogen atom that I'm talking about. There's more electrons for heavier atoms, but basically the fact is that the atom further breaks down into something like a nucleus, around which there is an electron, and the nucleus actually further breaks down into proton and neutron and things like that. So these types of small scales where particles exist, where the units of matter exist, is where we get into the quantum side of things. And it turns out that the physics of the very small is very different, and people kind of wanted to have a treatment of this physics as well. And they got inspiration, of course, from everything that was happening in classical physics, but they wanted to have a formalism and a way to describe with equations for something like the equation of motion of something like an electron, as small as an electron. So pretty much in physics, this is quite a bit of a theme that you'll notice, where you will see that we want to describe and predict where something will be. Okay, so we want to know, like, let's say we know the position of the moon right now around the earth. We want to predict where will it be in 10 days, maybe in 10 years, maybe in 100 years. Okay, and actually, you could do that mathematics, and you could do that physics of that pretty, you have the tools for that with something just like Newtonian mechanics. You can pretty good approximation of where the moon will be in 100 years you can get, actually. So you don't even need to really consider general theory of relativity to say something to have a solution for something like that. Okay, now let's say you want to go and have a bit more precision, and you want to understand something about some stars motion around a black hole very far away, concerning much bigger distance. Then you might need to consider something like general theory of relativity to describe that. But we are, generally speaking, we like to have an understanding of the behavior of these systems and be able to understand what is the equation of motion, what is the other way to say it would be, what is the position of some object as a function of time. For example, just saying that's a pretty basic thing that people liked to be able to understand about and write down and have the math and know which laws of nature kind of govern that. Like, so for example, we know the moon is gravitationally attracted to the earth, and it is very much in an orbit around the earth because of earth's gravitation. The earth is in an orbit around the sun. So basically, the earth's movement is governed a lot by the sun's gravitation, and there's some law. We put it into an equation, and we understand where the earth will be around the sun, or where the moon will be around the earth. And we have ways to write these things down. We have equations for all this, and depending, again, like I was saying, you could do it with Newtonian mechanics and get a pretty good approximation, and you might not need relativity, all the time. But sometimes it's good when you want more precision types of answers. It's good to incorporate general theory of relativity, because Newtonian mechanics is only an approximate answer. The more correct version of gravitation is given by general theory of relativity. So this is all to say that these theories ultimately are giving us a way to postulate and capture sort of a law of nature within equations, and that helps us to predict where something will be and know the position of some object as a function of time. That is one of the big goals of physicists historically. Okay, now I'm not saying that's the only goal, but just kind of imagine when you're starting off, what is sort of a goal. This is a pretty good goal. So now, coming to the small things, just like I said, we can know the position of the moon as a function of time. We might be interested in knowing the position of an electron as a function of time. Okay, so people were interested in doing that. They were used to being able to formalize and write down equations for things. So the moon is a classical object. We have a way to understand its behavior, its motion. Why not an electron as well? So think about the electron now. So because of how people operate and things like that, people are used to doing that in physics. So there is an entire field that then got developed with this type of goal. Now there's more goals, but this is a main one. Okay, quantum mechanics is basically writing down equations of motion for something based on the laws of nature that we know about that thing and what governs that thing. So now let's say we've got an electron. It could be a free electron. It could be an electron that's bound by a nucleus within an atom. Let's say it's just the hydrogen atom, to keep things simple, because the hydrogen atom just has the proton in its nucleus, and of course depending on the isotope of hydrogen. But it will, that electron, if it's within the atom, it is bound to the nucleus in some way or shape. There is some law of nature there that is keeping that electron in that atom. Or if it's just in space, just chilling, that's a different matter as well. But now let's try to understand what we can do where do we start with trying to write something down. So this is what they thought about in the 20th century. And there was this thought and this feeling that physicists had, which was to say that, well, you know how they already had some quantum mechanics going, actually. they had some quantum exposure going already in the sense of the photoelectric effect. So as you know, light has a wave and particle duality. And so light has a wave nature as well as a particle nature. And this was shown in the photoelectric effect. And we got, sometimes this is called the old quantum mechanics. So even though quantum mechanics ultimately focuses more on the matter particles, actually light gave us a really nice way to launch into quantum mechanics because light has a particle nature. So now, because light has a both particle and wave nature, people started to wonder if matter particles too might have a wave and particle duality. So maybe matter particles too have wave and particle nature at the same time. So that kind of inspired somebody like de Broglie to write down matter waves. So he came up with this idea of what if matter also has a wave nature and we can write something down about matter waves. So he came up with that idea. So we credit that to de Broglie. And the way you spell de Broglie is D-E space B-R-O-G-L-I-E. Okay? So this is this guy de Broglie. So then what happened was Schrödinger, somebody that a lot of people have heard of because of the Schrödinger cat, story, joke, whatever. This guy then actually wrote down for the first time a wave equation for a quantum or a wave equation for an electron, something like an electron, something small like an electron. So this was the first time that we got totally nicely a wave equation for something that small, which would basically give us something like its mechanics, like its position as a function of time, for example, right? So this type of mathematics was given to us by Schrödinger, and people liked it. People were like, okay, you know what? This is good. We can do something with this. We can start to do some writing down of equations and mathematics of something as small as an electron. And we think that the electron being a sort of a wave makes sense somehow because the electron is really tiny. Light is made up of photons at the quantum level. Electron, photon, these things maybe there's a wave nature to these things, and we will write it down like that. So then another thing that was really nice about Schrödinger's wave equations was that they actually had a really amazing sort of success in the sense that when you solved Schrödinger's wave equations, the solutions you got basically corresponded to the energy states we saw in the lab. So they had an experimental success as well. So we learned in chemistry about electrons being in orbitals around the nucleus, and basically these orbitals are at different states of energy, quanta, like basically there's a quanta of energy jump that the electron is making between these orbital levels and whatnot. And so when Schrödinger wrote down the wave equation for an electron with this sort of nucleus law of nature binding the electron description in that equation, what they got was something that corresponded with and made sense with what we were seeing in the lab. Because remember that quantum mechanics, of course, had success in the laboratory as in experiments. Because if none of it had any success in experiments, then it would have been gone by now. It was actually on the face of a lot of criticism that quantum mechanics survived because of its success in the lab. So this happened. And then what Dirac did, I'm just kind of quickly bringing you up to speed. So Schrödinger gave us the wave equation for particles, okay, for something like an electron. And then Dirac took Schrödinger's wave equations and turned them relativistic. So incorporating relativity into these equations gave us the relativistic version of these equations. So that was also really nice. We're making progress. We're not just kind of fumbling around, not knowing how to write things down and describe in the quantum world, which is the physics of the very small. But we are making some progress, some headway with describing things and formalizing things, and those things are even corresponding with what we see in the lab. So things are good. Things are good, except the only issue was that this wave equation thing, there were some confusions about it. People were like, well, you know, it looks good. It looks good on paper, and it's also kind of making sense with the orbitals and the excited states and energy states and the quantum jumps and all that stuff. But at the at the end of the day, this wave equation thing, it's kind of like dissipating across the universe. The wave equation was basically implying that the electron will just kind of disperse into the universe. If the wave is what that electron was following, if the position of the electron as a function of xyzt, all the dimensions pretty much, what was given by that wave equation, then as time proceeds, we're not sure where will this electron go. Like what it's kind of going in. It's that wave. And we're like, ultimately, something like an electron that is bound to a nucleus is most definitely localized. So we would want to see the mathematics also reflecting that. And even a free electron, we don't know if we like this idea of it just dispersing into the universe, like across the universe and just going away, right? That doesn't seem to, that doesn't, because they also saw the photographic plates, like electrons hitting photographic plates and leaving the streaks on there. And that looks like a pretty particle-y and tangible kind of thing. So they were basically struggling with the fact that there's a tangible, localized nature of these particles, but the mathematics is giving us a wave equation for the particle. So what exactly is waving? What is the wave here? And why does it make this thing disperse when we actually expect it to be kind of localized, especially if the electron is within a potential well of sorts, such as being bound to a nucleus. So this was actually the challenge, and people were very confused. And I don't think that they liked that there was this issue. It was sort of one of those things, like an elephant in the room, and it was a challenge. But then somebody acted very bravely and suggested something which forever just changed the landscape and changed how we think about quantum mechanics and changed how we indeed do things in physics. So up to now, the backdrop of all of this is the thing I was saying earlier, where when you have an object of any kind, whether that is the you or the me, a car, a house, the moon, or the sun, we like to be able to deterministically say where it is as a function of time and space. Even if the function is a very complicated one, we like to be able to solve it and get an answer in a deterministic way. But what happened with the electron is, even though it too is an object, I suppose, a very tiny one, turns out Max Born, so this is the guy who took this decisive step. Max Born said that actually that Schrödinger wave equation, which describes this electron, does not quite describe the position of the electron, but the probability of finding the electron. So actually, what you get as an answer from Schrödinger's wave equation, after you actually take the amplitude squared of the wave function, is the probability of finding that electron, not the position of the electron. So this is what I mean. Suddenly, physics took a very major turn and became probabilistic for the first time, at least known to me. For the first time, what we're getting as a solution or an answer for something, like where is this electron, we're getting a probability as the answer and not some certain value, okay? So this probabilistic nature of physics really threw people off and made them very unhappy, actually. I'm pushing my laptop away so I have more space. Many people, including the contributors of quantum mechanics, such as Schrödinger himself, were very unhappy and in shock when they realized that this is what's going on, that actually you are getting the probability of finding the electron, not the actual position of the electron. Now, the people who are, Niels Bohr, again, another person, a huge person in quantum mechanics, huge contributor to quantum mechanics, was probably okay with it, on board with it. It made sense to him. But to most people, it didn't make sense and they didn't like it. So then what happens next is, much to the dismay of everybody, Heisenberg, another guy in quantum mechanics, in Germany, of course, a lot of these people are Germans. He said he also was quite confused, confounded by this probabilistic nature and what it implied, because when you have a strange proposition, that generally also has implications. Basically, having a probabilistic answer means that you have an uncertainty in that answer. And he wasn't sure how to take it, how to really understand it. And look, now a bunch of people were just hating on it. They just hated the idea of probabilistic nature of physics, which is the quantum mechanics that we're talking of. But Heisenberg was particularly confounded in the sense that he was like, well, when we measure an electron in the lab, we are measuring an electron. We are measuring its position. So what do you mean that it's probabilistic and we will not know for certain what the heck is happening? Wherein is the uncertainty, and how do we quantify this uncertainty? Because probabilistic answer means that there is got to be some uncertainty, and I want to know what the source of that uncertainty is. And so he thought, and it dawned on him finally that actually the problem is that it's about measurement. The process of measuring where the electron is, what the position of the electron is, itself is disturbing the electron. Because, for example, if you want to know where the electron is, you might shine a light on it. Light has a particle nature. It is made up of photons, and an electron is a particle. So at the size of the electron, at the scales of an electron, the electron will see that light as another particle, and that light particle will have some energy, and it will hit that electron with that energy, and it will disturb that electron. So that electron will now inherit some momentum and whatnot. It will be disturbed. It will not be where it was before that measurement. So the act of measurement itself is changing the electron's position. So once you know the position, you don't know the momentum. Once you know the momentum, you don't know the position. One of those things is always going to be not known, uncertain. So there will be an uncertainty associated with any of these measurements. And what is that uncertainty is also something he quantified. So we will read that from the book. But basically, he realized, oh, because the electron is going to get a kick from that photon that we're using to probe the electron and measure its position, we now will have an uncertainty in the measurement of the electron. So the act, oh, thank you for the gift, by the way. Thank you guys so much for all your support and for the likes and the subscribes and everything like that. Please do. Once I finish my spiel, I will interact with the chat again, and we will also read from the book. But in the meantime, I appreciate the gifts and things like that, and I will read out the top fans in a minute here. So he realized that once you make a measurement, the act of measuring itself, such as with a photon onto an electron, by shining a light on an electron, you have disturbed the electron. So you no longer know both its position and its momentum with certainty. So if you don't know something with certainty, you have uncertainty. What is that uncertainty of this measurement is something he quantified, and we will read exactly. It's a pretty simple equation that gives us that uncertainty. But now, not only have we accepted that there is probabilistic nature of this math, and quantum mechanics is probabilistic, we're only getting the probability of finding the electron. We're not getting the position of the electron with those Schrödinger wave equations. Plus, there is an uncertainty associated with every measurement. Every measurement comes with an uncertainty that is inherent to nature. It is not an uncertainty coming from our dumbness or our lack of being careful. It is not a flaw of the experiment. It is not because we don't have the instrument that is precise enough for the measurement, but it is an uncertainty that is inherent in nature. It is intrinsic of nature. Nature is saying, you cannot know my position and my momentum at the same time, darlings. You just cannot. And we can do nothing about it. We just have to digest it like a piece of information. And people did not like that. Remember, all of the people that are not actively contributing, and even some of the people who are actively contributing to quantum mechanics did not like it. They were used to classical mechanics where you knew for certain. They're like, we can tell where the moon will be in 1,000,000 years. And you're telling me that there is uncertainty associated with the position of an electron, and that even when you have this equation and the wave equation, you only know the probability of finding the electron. They were just like, what the heck is this math? And what the heck is this quantum mechanics? This is a bunch of nonsense. So a lot of people thought that quantum mechanics was just, now we've just got off the deep end and this is making no sense, and people did not like it at all. This exact thing that I just mentioned above about the probabilistic nature of quantum mechanics and uncertainty principle, which have now been formalized and mathematically described. So now this is part of the formalism of quantum mechanics, not just words and things that people are saying, but it's a part of the quantum mechanics math. When you go to school for quantum mechanics, you learn it and you have to apply it. Now that this happened, the classical physicists were feeling very rebellious, and they were feeling very like, what is this nonsense? This makes no sense. Because ultimately they're saying that this is the science of the matter, right? Electron is ultimately a fundamental unit of matter. Electron is within the atoms. We're all made of atoms. Even the moon is made of atoms. Even the sun is made of, well, the sun is actually made of, I would say, nuclei, things like that. So how come you're saying that there is probabilistic nature to understanding all this? And how come you're saying there's an uncertainty associated with these measurements? Is the moon actually not there, and it's only there when I look at it, and when I'm not looking, it's not there? So there is this sort of famous thing that people thought of. I think Einstein was part of it, is that they're like, okay, so are you saying that when I measure the moon, with my eyeballs, because I looked at it, is there, but as soon as I don't see it, it could be maybe not there. There's an uncertainty associated with it, so maybe it's not there. You know, things like that. So there was a lot of debate and drama between the classical physicists and the quantum physicists. People were at each other's throats. People were putting, so this is where the cutthroat thing comes from. I mean, I made that part up. I don't know. I don't know if that's where cutthroat comes from, but physicists are pretty cutthroat. So physicists will, you know, debate and cause drama all day long, every day and twice on Sunday, and debate you to the death if they have a reason to. Okay, and now that they really thought that they have a reason to, they're like, oh my God, this is so bizarre. We're gonna critique this to death, and that's fine too. Every new development, every new discovery does get a lot of criticism, does have its share of critiquing. So that's nothing new. So you will see some famous scientists, when we read the book, you will see some famous scientists getting critiqued. I mean, Einstein got critiqued. It's not like every physicist, big or small, even I, we have all been critiqued. We have all shed tears of, what do you call it? Tears of, what's the word? When you are publicly humiliated. When you are publicly humiliated, right? See, a dissertation is supposed to be, for example, public, right? And what happens in a dissertation? You're grilled until you can't answer the question anymore, right? So public humiliation is part of the territory in physics. And so there's kitty cats playing here. So that is what happened. You will see from the book, when we read it, two famous people, big physicists. It happened to Niels Bohr during a debate between him and Einstein. So we will read about that dramatic occurrence and things like that, because people were very mind blown by, very mind blown by this uncertainty principle and probabilistic nature. They did not like it at all. Now I keep stressing that point because I want you to remember it when we talk about superstring theory later on. Not in this live, but I'm sure we will talk about it again at some point. We have talked about superstring theory in the past. Thank you for the gift, Tasty. We have talked about superstring theory, string theory, grand unification theory, unified field theory, all that stuff in the past, and it will come back up again. We will do it again, you know, stuff like that. But this issue that we are discussing right now of what they didn't like about quantum mechanics is one of the motivators for a unified field theory. All these bizarre properties of quantum mechanics, more like the implications, right? The bizarre implications of quantum mechanics is something that people had a major distaste for. Quantum mechanics is an experimental science, okay? It's been shown with the hydrogen atom, and there's lots and lots of experimental success of quantum mechanics, including discovery of all of the particles, the standard model, even, you know, the Higgs was discovered. Quantum mechanics is not just a theory. It has led to all of particle physics. So pretty much quantum mechanics, if it was not successful, it would have been dead by now because it was so bizarre. I'm telling you the story of how much people did not like it at all, and its implications were so bizarre. And because it's experimentally successful, it survived and gave us all of particle physics, which of course now we know there are leptons, quarks, bosons. Those are the particle families. And we have lots of quantum properties of things, and those have all been, yeah, it's all been, we have big experiments. You can look up the Large Hadron Collider, CERN. These experiments would not be a thing if quantum mechanics was not experimentally proven, okay? These are lots of money that's funded these types of experiments, and you always have to show a lot of goodness in your experiments in previous generations for a big experiment like the Large Hadron Collider to even exist, okay? So like, for example, Fermilab outside of Chicago. I think Fermilab has maybe a smaller accelerator. So there, you know, there are labs that are much smaller, have much smaller colliders than the Large Hadron Collider. So the Large Hadron Collider became famous doesn't mean it's the first of its kind, okay? It would never be built if there were not experiments that had shown things prior to it, and shown a lot of goodness and promised more results with more money. And then they built the Large Hadron Collider, okay? So definitely a very, 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 very experimentally successful. And so it survived. And not just now and later part of the 20th century, of course, it saw a lot of development. But even back then, even in the time of like Einstein and Niels Bohr, the way Niels Bohr was explaining the hydrogen atom was one of the first big sort of successes that they saw. And they were like, oh my God, like, yeah, I mean, the hydrogen atom, I mean, why they pick hydrogen atom is also the simplest atom. But you know, hydrogen, people understand, like that's chemistry. So like when quantum mechanics tallied up with chemistry, people really took it much more seriously. And there were kind of two camps, one camp of classical physicists and another camp of quantum physicists, okay? But do remember about this struggle and this distaste that a lot of people, especially the classical physicists, had for the bizarreness of quantum mechanics, because we will touch upon it again when we talk about superstring theory and its motivation, because superstring theory is motivated by this sort of bizarreness, and it wants to do a better job of explaining things and kind of be the overarching theory that contains quantum mechanics and gravitation. Because of course another flaw of quantum mechanics that I haven't mentioned yet in this live, but we've mentioned in the past, is that of course it does not explain gravitation. Okay, so the fact that it does not explain gravitation and the fact that it has so many bizarre properties is a major motivation for superstring theory and other unified field theories. Okay, keep that in mind for our later discussion on that. So now let me quickly look at the chat. Sorry guys, it's moving and I haven't looked at everything, but if you have questions, put it in the chat and do keep on dominating the chat. What happens when you... Hello, Stainless. You look absolutely amazing tonight. Oh, hello, Mark Heldman. So we will continue with the quantum mechanics. Thank you, Herbus Fumigas, undoubtedly subscribing. Please do. I'm smart with you too. You got this. Thank you so much. Please do subscribe so that I can see you again in future lives. See, we talk about these topics a lot. And if you're sort of only catching one of the lives, it won't make sense because we continue these topics. They're sort of multi-part episodes here. So currently we're on the quantum mechanics multi-part episode. So everything I kind of summarized so far up to the uncertainty principle, we actually covered in detail in the past live, in the last live. And then before that, we talked about, relativity and things like that. So we keep on going. So I hope you subscribe and can come back and join the conversation again, because that would help a lot to kind of keep with the flow, and also tells me where you're at with these topics and whatnot. Thank you. Whoop-de-doo is saying. Oh, thank you, whoop-de-doo. Thank you, Stainless. Thank you, Tasty Fisher. Thank you, Robin. Thank you, Quantum Mechanics as canonical. Thank you, Dialectical. Thank you, John Null. Thank you, Audalune. Some of these comments, my God. Hello. Higgs is H-I-G-G-S, okay? Higgs boson. The spelling is with 2 G's. I know, I hope that this topic has been interesting to a lot of people, even if you're a non-physicist, because quantum is, of course, increasingly relevant in computing. People want to understand it. I hope you engineers out there are making progress with quantum computing, so please do pay attention, okay? These fundamental topics are actually very important in our day-to-day life and whatnot, okay? So hang in there, pay attention. If you have a question, let me know. We will discuss this again and again, so don't worry. After hearing it multiple times, I think it gets much clearer. Thank you again to the gifters. Thank you, Tasty Fisher. Thank you, everybody. I have a super chat goal to help me with sustaining the channel. Even if you cannot do the goal amount, any amount is, of course, always appreciated. Not all energy is associated. Hello, Adeline. Ooh, I know what I'll do. I'll read the top fans. The moon is not an electron. So I love this comment by Sumit Oberoi. So it is true. So some people are actually okay with that discrepancy that I talked about, where basically there is the classical world, which is big stuff like trees, homes, cars, people, even dogs, cats, moon, sun. And we use classical physics to describe that world. And then there is the small world, which is electrons, atoms, protons, neutrons, you know, and we have the quantum mechanics for that. So some people are okay with this division of physics where they're like, okay, it's fine that this uncertainty principle and quantum stuff is a thing for quantum mechanics, which is the physics of the very small. And it's fine that classical physics works for the other stuff, which is the physics of the very big. So some people are quite okay with that. And oftentimes the people who work on these two things don't have to meet each other because they're in completely different fields. Like say if you're, you know, in the lab working on materials or at the very quantum level of stuff versus if you're an astronomer who's only interested in larger things, right? So pretty much a lot of the times, like say, if you do astronomy, cosmology, you might really need to understand about general theory of relativity, but maybe you don't know all the particles and all the particle jungle and whatnot, right? So maybe you never need to deal with that side of things, and it's okay. Now, actually, you do sometimes need to deal with that side of things. So you know, for example, we might want to know the nature of dark matter. That could be regarded as a particle physics question or an astronomy or a cosmology question. So, you know, there is actually some overlap, but oftentimes people kind of ignore it and say, you know what, I belong to the classical world, or you know what, I belong to the quantum world. In fact, people kind of dividing up in that way may even be the reason why we don't have a proper unified field theory, because, you know, we do really actually need to understand all of it to come up with a unified field theory, right? Now, there's also a question of what would the unified field theory do? Is it even, you know, worth it to work on one? Like, what does it do? What's the practical need of it in physics, right? Like, even if we did have a God equation, does that help us to understand nature in a fundamentally physically significant way? I mean, you know, we can talk about those things. Those are further details on that topic, but basically, a lot of people have been able to basically, you know, live with this discrepancy by ignoring it. They just ignore it. Like the physics of the big people just ignore the physics of the small people. And for almost a century, that was the case, or not a century, I would say for a number of years, and maybe even now, people ignore it. When people started to not ignore it properly and really think about it is the development of superstring theory, okay? So superstring theory wants to bring it all together and come up with something more general that can explain both general relativity as well as all of the particles. And we will talk about how that is actually very, very difficult, because the more progress we make in particle physics, the more you would have to explain with superstring theory. So it's not a trivial job at all, okay? But tonight is about quantum mechanics, so I don't want to get too distracted, okay? So let's keep on going with the quantum mechanics. Let me just update the title. Hello, Marco Polo. Are you asking if this is AI? By the way, if very relevant in computer science. Oh, good. I'm glad people are finding this to be relevant for computer science, because it really is. If you have a question and I miss it, please let me know. So the unified field theory, somebody asked, is the unified field theory like a fabric that is stretched by mass? So general theory of relativity is basically saying that gravitation curves space-time, and a massive object is basically bending space-time, and gravitation is that fabric of space-time. The unified field theory, well, it depends which one. The superstring theory is a candidate for the unified field theory, and it has this notion of a string and sort of different modes of that string that will explain different types of particles and things like that at a general, more fundamental level. So it kind of takes general theory of relativity and adds on to it and requires extra dimensions. So so yeah, by the way, we have talked about that as well in the past. If you are feeling impatient about superstring theory, then we have actually covered it in the past, and you can go look up those lives, but we will also bring it back again in the future here as well. But I do have a lot of live episodes all recorded and ready to go and posted under the live tab of the channel. So subscribe and go check those out when you can, because lots of things are covered there already. So now what we will do is rename this really quickly. And if I cannot see your chat message because it's moving too quickly, then I do apologize. And if you do a super chat, even if it's a small one, then it'll definitely highlight it for me. Okay, just letting you know that I don't mean to ignore you. It's just a little tough. So quantum, I'm naming this Quantum Drama with Oindree and Baji. Live study with me. Quantum, I think that's a good name. Quantum Drama Hi, Shy Guy. Hi, Wildery. Hi, Lazy Algorithm. Hello, Carlos. Hello, Not by Chance. CIA Training. Beauty and Brains. Thank you, Doc. RC Adventures. Binary Launch Codes. Thank you, Herbis. Thank you, John Null. Who are you, says Carlos. Well, I am Ninja Fist! Ninja Fist has done a super chat to say love the lipstick. Oh, thank you. I've forgotten which one this is. This might be, I think it's Lakme. But yeah. Thank you, Ninja Fist one. Love the lipstick. Thank you. Thank you for doing a super chat, Ninja Fist. I appreciate you. So, this is saying quantum drama with Oindree and Baji. I'm going to save it. We can do that. Yes. Quantum is what? Physics. Quantum is part of physics. Quantum mechanics. You look like my doctor in Fairfield. The God particle we might not get to tonight, but that's a great question. Keep that coming. Next time, remind me. Give me one more second. Yeah, feel free to remind me. Definitely remind me. My background is in physics. Physics and physics. I have 3 degrees in physics. Hello, Unspoken. My focus was more particle astrophysics, but the overall topic is physics that I studied. Quantum drama with Oindree and Baji. Okay. Okay, I saved that and I changed the thing here. Okay. Save. I updated the live's title. Sorry, guys. Yes, I'm drinking from all the big Stanley cup. I was part of the Anita experiment, not Ice Cube. And I was supposed to do a postdoc for Ice Cube, actually, but I took a different job. Whoops-a-daisies. Physics is the study of the spiritual. Thank you guys so much. Dominate. Hello to Korea. Hello to Korea. Hello to everybody. Hello to Antarctica, South America, North America, Africa, Asia, Europe, Australasia, especially my Antarctica. And everybody, thank you so much. Can we get 100 likes? Yes, please dominate the chat. And okay, now I'm done with the stream, what you may call settings. Thank you, Ariel. Thank you, thank you, thank you. Thank you, Whoop-de-doo. Thank you, Ariel. Thank you, KHI. Thank you, J-Man20. Thank you, Carlos. Thank you, Ninja Fist. Parallel universes, huh? What are you working on right now? We can talk about that at some point. So, I'm also here to learn myself. So, okay, I think I've done. Carlos is carless. Oh, okay. So, I kind of caught you up to the uncertainty principle, and then we will now go towards what happens next, and we will read about the drama from this book here by Michio Kaku, and the book name is Einstein's Cosmos. I was not able to find the book link because sometimes I'm able to link the book, but the book that I am reading, but sometimes it's not there. But I'm telling you in words. It's Michio Kaku's book. Oh my god. It's Michio Kaku's book. It's cold, so I turned the heat on. It's Michio Kaku is the author, and Einstein's Cosmos is the book. Where is the... Is the thingamawitch not working? I'm trying to see. I'm trying to see the thing that I want to... Oh, there it is. There's my link. But I don't think I can find... Let me quickly see if Michio Kaku's book can be linked here. Oh, there it is. So God Equation by Michio Kaku is something I can link. But the exact book that I'm reading from tonight, I don't really see. But you can find it elsewhere. That's okay. Anyway, I looked. Hi, Crazy Sick Wine. My dear Olive. What is Olive? Hi. Okay. So, we will keep on going. All right. Thank you for your patience. Now we will keep on going after this uncertainty principle became a thing, okay? So listen up and pay attention. And keep your questions coming and dominate the chat. So this was the decisive moment. So just after, so let me back up a little bit. Heisenberg reformulated this question into a new principle of physics called the uncertainty principle, which states that one cannot determine both the location and the velocity of a particle at the same time. More precisely, the product of the uncertainty in position and momentum must be greater than or equal to Planck's constant divided by 4 pi. So now we have a quantification of this uncertainty in quantum mechanics. It's not just a theory or just an idea. It is a quantified uncertainty which is intrinsic to nature. It is not a flaw of the experiment or the measurement, but the fact is that by the act of measurement, you have caused this uncertainty, and that uncertainty, there is a value of it. Okay, so this was not just a byproduct of the crudeness of our instruments. It was a fundamental law of nature. Even God could not know both the precise position and momentum of an electron. This was the decisive moment when the quantum theory plunged into deep, totally uncharted waters. So this is where the drama really begins, and what I was saying earlier, where people did not like this at all. Up to then, one could argue that quantum phenomena were statistical, representing the average motions of trillions of electrons. Now, even the motions of a single electron could not be definitively determined. So this situation of uncertainty was very horrifying. Einstein was horrified. He almost felt betrayed, knowing that his good friend Max Born was abandoning determinism, one of the most cherished ideas in all of classical physics. See, I told you how this was the first time when this probabilistic stuff was happening, and probabilistic nature of physics and uncertainty principle was being embraced and formalized for the first time in such a big way, where it's not just an idea, but mathematically we are accepting it. So he felt abandoned by that. He felt like, oh my gosh, are we going to be all probabilistic now? He didn't like that. So determinism states, in a sense, that you can determine the future if you know everything about the present. For example, Newton's great contribution to physics was that he could predict the motion of comets, moons, and planets via his laws of motion once he knew the present state of the solar system. For centuries, physicists had marveled at the precision of Newton's laws, that they could predict the position of celestial bodies, in principle, millions of years into the future. In fact, up to that time, all of science was based on determinism. That is, a scientist can predict the outcome of an experiment if the scientist knows the position and velocities of all the particles. Pretty much, if you know the position and velocity, now you should be able to predict a state in the future, the state of the system in the future. That's pretty much the deterministic approach. People, it's almost like they had a bit of a control freak nature. They want to be able to, from the state now, they want to be able to predict the future. And if they cannot predict the future, then they feel uneasy. Okay? So that's that deterministic approach. Whereas quantum mechanics is much more of a submission to nature doing its thing. It's a surrender, if you will, and not trying to predict and control every little thing, quite literally, right? So not something that they were used to. In fact, up to that point of time, all of science was based on determinism. That is, a scientist can predict the outcome of an experiment if the scientist knows the position and velocities of all particles. Followers of Newton summarized this belief by comparing the universe to a gigantic clock. God wound up this clock at the beginning of time, and it has been steadily ticking ever since, according to Newton's laws of motion. If you knew the position and velocity of every atom in the universe, then you can, via Newton's laws of motion, calculate the subsequent evolution of the universe with infinite precision. However, the uncertainty principle negated all of this, stating that it is impossible to predict the future state of the universe. Given a uranium atom, for example, one could never calculate when it will decay Only the... Oh, hi, Baji. Oh my gosh. Baji scared me. Hi, Baji. Only the likelihood of it doing so. So we won't deterministically know when the atom will decay, the uranium atom, but only the likelihood of its doing so. Okay. That's Baji, and he kind of startled me. In fact, even God or a deity did not know when the uranium atom would decay. So basically what they, I think, hoped for is that quantum mechanics will give us answers, not uncertainties. It will give us solutions, not probabilities. They're like, if you're working on quantum mechanics and developing quantum mechanics, how come you can't tell me what will happen in the future? You better be able to predict what happens with this atom thing in the future. And if you cannot do that, then what have you done? What is this quantum mechanics theory? You know, what is this? Why can't you tell me what will happen? You should be able to, because that's what they were used to. Deterministic classical physics and classical physicists were used to coming up with a theory or an equation or a set of equations that will predict the state of a system in the future. Once you know the present status and certain things about the present status, like positions, velocities, whatever, then you should be able to, utilizing physics, be able to give us the future and future state. And that too, you should be able to predict things, and it should be a deterministic prediction. And, you should be able to measure that, and that measurement should be, totally certain. All this probabilistic stuff says that you won't be able to really know what will happen in the future deterministically. And this was very uncomfy for these people. They were not used to that. This was an uncomfortable thought that we would not be able to predict deterministically the states of these things. There will always be inherent probability and uncertainty. So people were like not comfortable with this, okay? So, okay, so now things are gonna get very exciting. I love this part of the book. Hi, Andrew. When it comes to quantum physics and time travel, is it possible? And I have a second question. Time travel is possible at the particle level. For microscopic things, time travel is possible. For macroscopic things, time travel is usually not possible, as in not logistically attainable. But time travel in particle physics is possible and quite mundane. Okay? I like this comment. Time Guy is saying baddies are learning quantum mechanics now. Now we gotta get jacked, rich, and smart. Cooked. Whew, I'm a little cold. Can we get 120 likes? Hello, Lewis. Okay, so now comes the dramatic part, which I love very, very much. So I will be reading with gusto. In December 1926, responding to Born's paper, so remember Max Born is the guy who gave us probabilistic nature of quantum mechanics, Einstein wrote, "Quantum mechanics calls for a great deal of respect, but some inner voice tells me that this is not the true Jacob. The theory offers a lot, but it hardly brings us any closer to the old man's secret. For my part, at least I'm convinced that he doesn't throw dice. So Einstein is saying that God does not throw dice. This probability business cannot be the real explanation of nature. There has to be something bigger that can tell us about nature more fundamentally, more generally. And I want to get to that. So Einstein was very motivated to find a unified field theory or the grand unification theory. Why? Because he wants to read the mind of God. He wants to know what is the ultimate nature and the ultimate explanation. He's not happy with this probabilistic nature and all these probabilities and quantum mechanics stuff, okay? When commenting on Heisenberg's theory, Einstein remarked, Heisenberg has laid a big quantum egg. So Heisenberg gave us the uncertainty principle. In Göttingen, they believe in it. I don't. Schrödinger himself disliked this idea intensely. He once said that if his equation represented only probabilities, then he regretted having anything to do with it. So even the guy who gave us the Schrödinger wave equation, so Schrödinger, really the wave equation comes from him, but then the fact that it only represents the probability of finding the electron and not the position of the electron, that is given to us by Max Born. So Schrödinger was deeply disturbed that his wave equations that he wrote down and had some success with ultimately turns into these probabilities. And really the way to look at the wave equations is that they represent probabilities. The chance of finding the electron is waving, not the electron. Okay, so, but he didn't like it. He didn't like it. He didn't like that the solution was a probability. Okay, that was just too much for these people who are, they're contributing to all of this, but something so bizarre is too much for them to digest. So physicists were beginning to divide into two camps. Einstein led one camp, which still clung to belief in determinism, an idea that dated back to Newton himself and had guided physics for centuries. Excuse me. Schrödinger and de Broglie were allies. The other, much larger camp was led by Niels Bohr. So this is Niels as in Niels, Bohr, Bohr. Okay, who believed in uncertainty and championed a new version of causality based on averages and probabilities. So Niels Bohr is like embracing the probabilities, championing the probabilities. He's like with it. He is leading the quantum phenomena. So as you can imagine, these two are going to have a public debate and it will get very dramatic. So I love this part of the book and I'm going to read that. Bohr and Einstein, in some sense, were polar opposites in other ways. While Einstein as a child shunned sports and was glued to books on geometry and philosophy, Bohr was renowned throughout Denmark as a soccer star. Apparently, Bohr was athletic. Whereas Einstein spoke forcefully and dynamically, wrote almost lyrically, and could exchange banter with journalists as well as royalty, Bohr was stiff, had a horrible mumble, was often inarticulate and inaudible, and would often repeat a single word endlessly when engrossed in thought. So two very different people. Einstein was more extroverted, more socially adept, very charismatic, and Bohr was a bit of a socially a bit reserved and struggled a little bit. While Einstein could effortlessly write elegant and beautiful prose, Bohr was paralyzed when he had to write a paper. which is also not a good thing if you're a scientist, because you want to have your work be out there. As a high school student, he would dictate all his papers to his mother. After he married, he would dictate them to his wife. He would sometimes involve his entire laboratory in rewriting his papers once over 100 times, completely disrupting the work. Sounds like quite the nightmare of an advisor, if you will. Hi, Anita. Hi, Andrew. Autism versus pure savant. Yeah, Einstein was really good publicly. I looked up and it was 3, 2, 1. I love this topic. Thank you, Flair Ryan. The cat in the box guy. Yes, Schrödinger is the cat in the box guy. Let's see. A deviated septum? I don't know. The marble. This granite thing. This is my kitchen counter. You guys are funny. Baji has gone upstairs, so it's too cold down here for him. The upstairs is warmer. Where was that one comment? Anita, can I get a shout out? I just joined this cool stream. Hello, Anita. I hope that you're still here. Okay, so Bohr was a very difficult advisor. He struggled with communication, it looks like. He was kind of introverted, kind of reserved, and rewrote his papers a lot, made other people rewrite his papers. Not charismatic like Einstein. Einstein was like a very good communicator, writer, speech giver. He would do public appearances and give these big, great talks. So Einstein communicated his science really well, and he wrote really nice, succinct papers, his 4 big contributions of 1905. He published them all in that year. He's like a very good, honestly, Einstein was the whole package. He was that awesome scientist who also did awesome communication. And honestly, I think that's what makes him Einstein, right? Because I feel like there's a lot of smart people who just might not have the smarts of communication, and those people we know a lot less about, okay? Anyways, so he would sometimes, this Bohr guy, Niels Bohr, he would sometimes involve his entire laboratory in rewriting his papers once over 100 times, completely disrupting the work. Wolfgang Pauli, so you guys might have heard of the Pauli exclusion principle. That's from this Pauli guy. Pauli once asked to visit Bohr in Copenhagen, replied, "If the last proof is sent away, then I will come." As in, he's thinking that the last proof, as in the last draft, will never happen. So he's like, well, I'll come when your last proof is done. Both were, however, obsessed with their first love, physics, which is Einstein and Bohr. Both loved physics. Bohr, in fact, would scribble equations on the goalpost of a soccer game if he had an inspiration. Both would also sharpen their thoughts by using others as sounding boards for their ideas. Strangely, Bohr could only function if he had assistants around him to bounce off ideas, Without an assistant whose ear he could borrow, he was helpless. The showdown finally came at the 6th Solvay Conference in Brussels in 1930. So the year is 1930. It's been 15 years since general theory of relativity has been published. So there has been some socialization of general theory of relativity, and Einstein is quite famous. He is a well-known, renowned physicist of his time. And Niels Bohr is the head of the quantum mechanics camp, although also very successful and notable physicist. People remember, a lot of issues with quantum mechanics. So there is going to be a showdown between Einstein and Niels Bohr, and we will discuss that. What was at stake was nothing less than the nature of reality itself. Einstein hammered incessantly, if I can say the word, at Bohr. So Einstein is like, the stage is mine. I have so many issues with quantum mechanics. I can't even. I'm going to show you who's boss tonight. So Einstein was like in his element. He's like, I hate this quantum mechanics stuff. Like, there's all these probabilities and uncertainties, and what have you done? Why can't you predict things? Why can't you be deterministic? Why you be like that? So he's like hammering at Niels Bohr, which is very common in physics. People hammer each other, people grill each other and try to find holes in your theory, poke holes at your theory. So that's what he's doing. So Einstein hammered incessantly at Bohr, who reeled under the constant attacks, but managed to ably defend his positions. Finally, Einstein presented an elegant thought experiment, which he thought would demolish the demon, which is the uncertainty principle. So here it is. Imagine a box containing radiation. There is a hole in the box with a shutter. When the shutter is opened briefly, so Einstein really thought about this, by the way. He's not just critiquing quantum mechanics as a hobby. He really thought about it. He really pondered it, and he didn't like it. So here's the thought experiment that he's challenging Niels Bohr with. Okay, so once again, imagine a box. So this is important, so listen closely. Imagine a box containing radiation. There is a hole in the box with a shutter. When the shutter is opened briefly, it can release a single photon from the box. Thus, we can measure with great certainty the precise time at which the photon was emitted. Much later, the box can be weighed. Because of the release of the photon, the box weighs less. Because of the equivalence of matter and energy, we can now tell how much total energy the box contains, also to great accuracy. Thus, we now know both the total energy and the time of opening of the shutter to arbitrary accuracy without any uncertainty, and hence the uncertainty principle is wrong. So notice how he's using a photon, which is a quantum scale thing, and all that stuff. And he's saying that the uncertainty principle cannot be right. Like, look at this. This is a thought experiment. This is something we can observe. This is something we can set up. Explain this. Explain where is the uncertainty in this. Einstein thought he had finally found the tool to demolish the new quantum theory, which is this theory. Uncertainty principle. So once again, he thinks that we now know both the total energy and the time of opening of the shutter to arbitrary accuracy without any uncertainty, and hence the uncertainty principle is wrong, because he's saying that there should be certainty for everything here. Where's the uncertainty? Paul Ehrenfest, one of the participants to this conference and a witness to this fierce battle, would write. So he's describing what happened with Bohr. Poor Bohr is getting grilled like hell with against his quantum mechanics by Einstein. To Bohr, this was a heavy blow, says Ehrenfest, because he was there at the debate. At the moment, he saw no solution. He was extremely unhappy all through the evening, walked from one person to another, trying to persuade them all that this could not be true. So he's like very sad now because he's like, somehow this could not be true. But no one's listening. Everyone thinks Einstein won. He lost the debate. He's so sad. So he's like, because if E was right, Einstein was right, this would mean the end of physics. So Niels Bohr is like very upset. But he couldn't think of any refutation. I will never forget the sight of the two opponents leaving the university club. Einstein, a majestic figure, walking calmly with a faint, ironical smile, and Bohr trotting along by his side, extremely upset. When he talked to Ehrenfest later that evening, all Bohr could mumble was one word over and over again: Einstein, Einstein, Einstein. Oh. But after an intense, sleepless night, so Bohr is thinking about what Einstein said, right? It's stuck in his head. He cannot refute it, but he's like very affected. He's like, well, Einstein can be right, but Einstein did say this thought experiment, and I couldn't figure it out. I didn't have an answer, but he's in his loop, basically, and he repeats a word, remember, when he's thinking hard. So he's like, Einstein, Einstein, Einstein. So he's literally so upset. I hope you understand. But after an intense sleepless night, Bohr finally found the defect in Einstein's argument. So Bohr is the underdog here. This is an underdog story that I love. Bohr, the underdog, did not sleep until he found the defect. And what is more, he used Einstein's own relativity to defeat him. So we will look at this. Bohr noted that because the box weighed less than before, it would rise slightly in the Earth's gravity. But according to general relativity, time speeds up as gravity gets weaker. Because remember, we're doing general relativity here too. So he's like, okay, listen to this again. Bohr noted that because the box weighed less than before, it would rise slightly in the Earth's gravity. But according to general relativity, time speeds up as gravity gets weaker. So, because time is relative. So that time beats faster on the moon, for example, right? The gravitation of the box is changing, which means that time is going to be different now, which is what relativity says. Remember, relativity gives us the relative nature of space and time. So if you've changed the gravitation of something, then you've changed its time and how fast or slow the clock runs in that system. And we don't usually care about these things because we live in the classical world and we don't do relativity. But if you did more precisely, then you would have to take into account relativity. So he's like, okay, so actually, time speeds up as gravity gets weaker. So that time beats faster on the moon, for example. Thus, any minuscule uncertainty in measuring the time of the shutter would be translated into an uncertainty in measuring the position of the box. You cannot therefore measure the position of the box with absolute certainty. There is uncertainty in measuring that position of the box because there is uncertainty in measuring time. And there is a change in how time works. Furthermore, any uncertainty in the weight of the box will be reflected in an uncertainty in its energy and also its momentum. And hence, you cannot know the momentum of the box with absolute uncertainty. When everything is put together, the two uncertainties identified by Bohr, the uncertainty in position and uncertainty in momentum, agree precisely with the uncertainty principle. So basically he's saying there's uncertainty in time, which gives you uncertainty in position, which is exactly what quantum mechanics says. And then there is uncertainty in energy, which translates to an uncertainty in momentum, which is pretty much puts together uncertainty principle. So uncertainty principle holds. Where Einstein was challenging the uncertainty principle, Bohr is proving that uncertainty principle actually does hold even in this scenario, because what he didn't think of earlier was that actually general relativity makes it so that uncertainty principle holds in this case, because we forgot about how time changes when the gravitation of something changes. And that would have to be taken into account. Bohr had successfully defended the quantum theory. When Einstein complained that God does not play dice with the world, Bohr reportedly fired back, "Stop telling God what to do." So they had this whole debate, which I think is very entertaining. Ultimately, Einstein had to admit that Bohr had successfully refuted his arguments. Einstein would write, "I'm convinced that this theory undoubtedly contains a piece of definitive truth." Commenting on the historic Bohr-Einstein debate, John Wheeler said, "It was the greatest debate in intellectual history that I know about. In 30 years, I have never heard of a debate between two greater men over a longer period of time on a deeper issue with deeper consequences for understanding this strange world of ours." So that is the Einstein-Bohr debate that I wanted to tell you guys about. Hopefully you enjoyed it. So Bohr is Bohr is spelled actually as B-O-H-R. Niels Bohr, okay? B-O-H-R, Bohr-Einstein debate. You can look it up and as well, but this was from that book. As far as we know, there is no end of the universe. Universe is infinite. Thank you, SDG, NOV. Thank you for the gift. I'm going to read the top fans in just a second here. Thank you, Ella. I love Elaine. Thank you for announcing your departure, Jesus, just like an airplane. Harbis is saying Bohr versus Einstein was almost as serious as debating who gets the last of the pigs in. This was so serious, and I love this story. Hello, Joshua. Thank you, guys. So, by the way, hi, Northern Versus. Did you like this Bohr-Einstein debate story? So anyway, next we will actually read about Schrodinger's cat and box situation, and certain sort of, so this was the great sort of defense of the quantum theory uncertainty principle that Bohr successfully did against Einstein and classical physicists who were, having an issue with this new quantum theory. But after that is done, we will actually now proceed to sort of some of the more bizarre implications of quantum mechanics, but we'll do that next time. Oh my God. So I just wanted to say that tonight we will end the topic with the Bohr-Einstein debate, and we will start it back up with more Schrodinger box and cat and all that stuff, and certain other Copenhagen, school of thought and quantum mechanics implications next time. There is some more interesting discussion left in this chapter that we will continue on, okay? So with that, I will put a bookmark. Why do you think I'm AI? I'm just so amazed by quantum entanglement. Hello, Dub Styles. So I'll put a bookmark and we will continue this next time, okay? I mean, some people think I have boogers. Does AI have boogers? Casimir effect. We have mentioned that in the past as well, but did you like it, Adeline? Adeloon? Thank you, Dub Style. So we will continue this topic next time, guys. I will read some more of your comments and messages now and chit-chat for a little while and then say goodnight, okay? What color lipstick? This is a red. I can look up the shade and tell you more specifically next time. Thank you, Time Guy 441. What color lipstick is that? Really striking. Thank you. I will let you know. I think it's either a Lakme or a Maybelline, but I can look up the specific shade and whatnot for you. Hello, Carlos. Thank you. Northern Versus is saying AI cannot see into your soul. I love that. Northern Versus, thank you. I loved your comment. Where is it? Northern Versus said, it excited me. That is such an appropriate comment, guys, because we just finished talking about quantum mechanics and excited states and orbitals and how Schrodinger's wave equation gave us that. And then Dirac turned them into relativistic equations, and then Max Born turned them into probabilities, and then Heisenberg gave us the uncertainty principle. And then Bohr almost lost to Einstein in a debate, but then Bohr won. I hope you enjoyed it. Chai coffee got banned? Oh no. What happened? So I haven't been following everybody's messages, so if you have a question, please do tell me or bring it up next time. We did cover the debate, high dialectical. It's a great story, read it many times. Oh, very nice. Nicodemus Morris, loved it. I liked it. Okay. You like M theory. Hi, Time Guy. What about looking forward to the next stream? Okay, very nice. We will definitely do more live streams soon here. So keep coming back. Please do subscribe so you can catch these lives. Please do subscribe so you can catch these lives. And also, I do have some pre-recorded videos that I stream in the premiere mode where you would see the chat be live, but the video of me is pre-recorded. This is not pre-recorded, this is a real live, but I do have some pre-recorded videos publishing as well with the live chat. If you see those, please show some love. There's Baji, he's back. Please show those videos some love as well. I really appreciate it. So yeah, if you see our shorts, clips, videos, pre-recorded, real lives, as in full lives, all of it is real, but some videos are pre-recorded. If you see those, please do show some love and leave your comments so I can read them and know your thoughts and things like that, okay? Thank you. What do I usually talk about? We usually talk about physics, cosmology, astrophysics, astronomy, and just in general chit-chatting. Thank you, K West. Are you from India? I am. What is that in the back? A cat tree? And Baji. He's climbing and playing with me in the background. Baji Baba! Oh, Baji, you climb so much. Oh, Baji! Baji's having a sneezy. It is so cold here. We're gonna go upstairs to bed so that we can be warm. Oh, Baji! Oh, Baji! Oh, Baji! Mama loves you. Mama loves you. Baji's here. Mama loves you. Thank you, guys. Please do like and subscribe. Can someone do a $20 super chat to help me with my goal? Oh, Baji, are you cold? Baji Baba is sad and cold. Oh, come, Baji. Stay with Mama. Stay with Mama. Stay warm. Stay warm with Mama. Baji. The gravitation here has shifted because Baji is jumping off of my lap. So time has definitely sped up. The gasps? Hi, Shakuni. I'm doing good. How are you? Okay, let me read the top fans, actually. I never did that. Ooh, number 1 is K West. Number 2 is Ninja Fist. Number 3 is Crazy Sick Wine. Number 4 is JKD Viper. Number 5 is Dialectical. Number 6 is Herbis. Number 7 is Thorfinn. Number 8 is Ray. Number 9 is, I can't quite read that name. Number 10 is Carlos. Number 11 is John Null. Thank you so much, guys, for all your support. Really appreciate it. I'm glad you enjoyed. And subscribe so we can see you again next live. Oh my God, I see a comment. 4.3 million solar masses. Aw. Thank you guys for all your comments on my other videos too, guys. Really appreciate it. Hi, fried rice. There is a doll next to my name. Ooh, thank you, Andres. I see Andres Garcia did a floating heart gift. Thank you so much. I hate... Okay. I'll focus on the love comments, not as much on the hate comments. Although I think the haters are actually secret lovers of mine. What's with the little doll? Okay. Thank you, Mark Heldman. Mark Heldman is saying you're a good person. Now, thank you. Thank you for being here on the live and enjoying. It's very encouraging. Happy to have your support. Levi Maxwell is saying hello. Hello. Huto is saying hello from India. Hello, Huto. Fried rice lover is saying no, she is not. Okay. Have a good day, Oindree. Aapka din subh ho. Thank you, same to you, Shakuni. Yay, thank you for subscribing, K West. We were just talking about quantum mechanics. You might want to rewind, please, Scooty Kong. I think you can rewind on the browser. Till the next live. Yes, see you soon. Yes, quantum mechanics. We had a really interesting discussion, so you might please do rewind. Okay? I'm loving the comments I'm reading on my other videos from you guys, by the way. It's very nice to see the engagement and people commenting with their related thoughts on the various videos. I really like it. Thank you. Aw. Unique Video says, hi sis, has subbed you. Thank you, Unique Videos. तुमने न जाना कि मैं दीवाना लेकर आया हूँ. Good night, guys. You can say your last messages and say good night, and then we will sign off. I will rewind to get a deeper understanding. Please do. Thank you. You can certainly rewind any part of the live. I do believe that the rewinding of a current live works on the browser, but I'm not sure if it's working on vertical live or not. But feel free to revisit any of the parts and let me know any questions in the comments, especially after the live posts. Feel free to put any questions or thoughts in the comments. Then I can see those easily after the live has posted, because sometimes I might miss one of the chat messages, but I can see the comments. But I also appreciate all your chats. Hi, Loch Ness. Loch Ness. I love it. If the universe is a series of Big Bangs. So we came from the Big Bang and expanded due to dark energy, which is a current research topic. So the Big Bang happened everywhere. There is no center of the universe at this time. That is now here, if that makes sense. If that was the Big Bang, that is now here. So the universe has the same universe that was tiny in the beginning has expanded to its current size. So, and it's also pretty much infinite as far as we know. So, there's no like end of it. You know what I mean? We're in the universe, so we don't know any end of the universe. And there is no central point. Okay? Hi, Hyan. Smart, gorgeous, and you can sing. I do like to sing sometimes, yes. Ho, ho, That's a nice favorite song of mine. Actually, there are other songs that I really like that I cannot sing as well. But this one I like to sing. There's different songs for singing versus listening. Baji Papa is here to give me company. So we have to go to bed soon here because we're getting cold. Hi, Baji. Oh, Baji. Oh, Baji. Baji. This is Baji Papa, kitty cat. A lot of dark matter in my eyebrows. Oh, you guys are funny. When you say we didn't come from the Big Bang, do you mean that actually we came from... So we did come from the Big Bang, but more specifically, we come from stars. Is that what you mean? Because then I agree. We try to be on at least a few nights per week. There is not a set schedule, but it's more common that we're live during the weekdays, okay? Mark Heldman. Please subscribe and have the notification bell so you can know when we're live. Thank you, Benito. She's so pretty. I wish her sanity and wellness. Thank you. Good night, guys. You knew me years ago? Where? Where did you know me years ago? तुमने न जाना कि मैं दीवाना लेकर आया हूँ दिल का नजराना मेरे दिल की है जो दास्तां सुनो ना सुनो ना सुन लो ना हम सफर मुझी को चुन लो ना सुनो ना सुनो ना सुन लो ना Thank you, Newman. Thank you, Kyle. So you don't know where you know me from? Well, I hope you know my channel. It's called Baji and Physics. And we cover physics, astronomy, cosmology. and kitty cats and me. Hello, Selectrovert. Hello, Gina. Gina, इसी का नाम है Gina. इसी का नाम है Gina. इसी का नाम है God particle. I don't know that we will definitely cover the God particle, but I'll certainly keep that in mind. Did you live in Illinois? No. I lived in Ohio and North Carolina. So you don't know where you know me from. So you might not know me. Oh, you want cosmology? Okay. Well, we spend a lot of time with cosmology, actually. I thought we'll take some time for quantum mechanics because that is really cool too. You know what I mean? But if you like my if you like cosmology, then we have a lot of episodes recorded on cosmology that you can go check out anytime. But we will certainly return to cosmology as well. We do that a lot. The camera's not shaking. I am, because I'm cold. Hi, silly boy. Thank you, Jamaican. You saw my Instagram. Thank you. I do love to travel. I actually have a TikTok with the same username as this YouTube, and I cover a lot of travel there. Thank you. So my TikTok is Oindree, same username as here. It's called Boston Girl, and a lot of my travel content is on TikTok. Instagram, I don't update too much, but it's also there if you want to add me there. Hi, Chosen Fire. I seem like blood. That's funny because most of the time I don't really wear makeup. I do have socks on because it's very cold. Get that money. What do you mean? Get money out of my mind? Because you're gonna do a super chat of $500,000? Let's see it. My chart. I don't know what you mean, Michael. Thank you, Rick. I don't want to ban him because he's helping my engagement. I don't want to ban him. He's helping my engagement. I am worth more than 500,000. This is true. But it's a start. We gotta get it started. This guy is probably from India and cannot handle an empowered, educated woman. So, honestly, not shocked. I don't really watch TV. No. Thank you, Carlos. So, I don't really watch TV, but what's a show that I've enjoyed in the past? I liked watching, I think it's called like Virgin River is a show that I like. It's set up, I think it's set in California in the show. Yeah, it's on Netflix, but I currently don't have Netflix anymore. So I think I like this. I like that show. It was very peaceful. I like peaceful content. I like peaceful content that there. You can have a little timeout. 500,000 in a couple of years might only buy a couple loaves of bread. I like that show on Netflix. Thank you, Ninja Fist. Love you too. Silly boy. We are finishing up, Justin, but you should rewind. We talked about quantum mechanics. Hello, British Bulldog. What do you mean? Have you experienced ego death? And if so, can you explain this transformation? What, because I put lipstick on? That's it? Well, yeah, I currently don't have any subscriptions, so I cannot think of a show really that I'm watching or anything. I've been just working a lot and doing content, consulting, you know. So I've just been busy and happy. Touch wood. And evil I remove. And thank you, universe. 4:09 in the morning. So I don't really watch TV anymore. I watched TV when I had a corporate job. Ever since I left, I don't really watch TV anymore. Prasad. I like to say touch wood, knock on wood. Happy birthday. Okay. All right, guys. Good night to everybody. Thank you so much for joining. You should rewind. BMCK, hello. Good night. God bless. Good night, everybody. I'll see you next time. If you see my videos, clips, shorts, please do show some love. Appreciate it. I was about to say something, but I forgot. Thank you. Love your spirit. Thank you. Good night. I just forgot. There was one more thing. Hi, Peter. Oh, yeah. I think, so this was a very interesting episode. You should definitely rewind and see it, Justin. Can you rewind on the phone or not? I think it has to be on the browser. Okay, well, enjoy when you rewind and leave me a comment when you've seen the whole thing, okay, Justin? Especially the physics part. Whatever you see, let me know your thoughts. Thank you, Chosen Fire. Appreciate you. Love you guys. Mwah, 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 mwah. Good night. Sleep tight. Until next time, okay? Bye-bye.